to my talk about writing TimeSeries database. You probably were wondering what TSDB means. It stands for TimeSeries database, and performance optimizations that we use when writing them. So my name is Khavronenko. I'm writing in Go for about like 6 years or something like that. But I don't consider myself as a professional developer. I'm a casual developer, so I play games after work instead of working on side projects. And for the last 3 or 4 years, I'm working on an open source project called Victoria Metrics, which is a time series database written from scratch in Go. So here we are on GopherCon talking about database written in Go. And before we discuss what time series, what optimizations we can use for time series database, let's understand what data needs to be stored in time series database. Let's start from very simple stuff, from the metric. So here you see some metric called Go info. It has a label called version, which states the exact Go version, and it has also value and a timestamp. So basically what this metric is, it is an observation of something, in this case of version, and we know its value and when this observation was taken. Okay, here we see multiple metrics displayed on one screen. These are metrics in Prometheus exposition format. You probably know of Prometheus. It is also a time series database written in Go, and it has this really cool Prometheus exposition format. Why it is cool? Because it's really simple to read for humans. You clearly understand what this slide means. And this page opens when you go to the web page of your application /metrics. This page is available when you include some Prometheus libraries in your application to expose metrics. And this is how you get this metric. So you don't push them, they're just available on the web page of your application. And to process these metrics, there are usually a separate application, which is called collector. And this collector periodically scrapes this metric. So it opens this /metrics page with some interval, like 10 seconds or every 1 minute. It processes all the data and sends it forward to time series database. And collectors usually processing not metrics for one service. They are processing it for thousands or hundreds of thousands of targets, and they do it periodically. Each minute, for example, they scrape and scrape and scrape in data, and then they send it to time series database, where this data is processed again, stored on the disk, and is available for read queries. Okay, and a bit of workload pattern, which is expected for modern time series databases. So here you see the ingestion speed into Victoria Metrics installation. It is about 17 million samples per second of constant ingestion speed. And here's the read request rate, which is much slower than ingestion, sorry. It is about 100 RPS for reading data. So from these two pictures, we can say that ingestion speed is quite stable, almost flatlined, while read request rate is quite chaotic. So you never know, you can't predict how it will behave, which time series will be requested by the user, which dashboard will be opened, when, for what value. And what conclusions we can make from this workload pattern is that time series databases mean to process tremendous amounts of data. That the time series databases are usually write-heavy applications. They are mostly optimized for ingestion and less for reading. And that read load is quite unpredictable in time series databases. You never know what user will want to plot, what user will want to display, and when. So how to build time series database, how to solve all these requirements for big workload? Well, 99% of your success will depend on right system design. And you can choose right system design if you know these preconditions, if you know what metrics are, what is expected workload pattern. So for example, you can choose LSM data structure to reduce write amplifications when you receive data. You can also, knowing what metrics is, you can use some column-oriented storage. So you know that you have metric names and metadata, which is strings. You know that you have values, and you know that you have timestamps. These are 3 separate columns They can be stored separately. They can be compressed with different compression codecs. They can be sorted differently. So you can benefit from columnar storage. And also, time series data is something that already happened in the past. So it is likely it will never change because observation was already made. So you can benefit from choosing some data structure which is oriented on append-only writes, because you don't need to modify metrics in the past. So you can squish something more from this design approach. But of course, recommendations about Go optimizations regarding system design are not really useful for us, for you as the audience, because you can't get back to work and apply some design recommendations, because probably you are not working with time series data, or probably system design is something like foundational you can change. So today we'll be talking about some non-design specific optimizations in time series data. And first of them is strings interning. So remember I talked about these scrapes that collector periodically scrapes metrics. And for example, this metric with Go version, it is likely to be repeated many times. And it is likely to be the same across these thousands and hundreds of thousands of targets. Well, probably not the same. Maybe you will have 5 different versions of Go, but not thousands. So, but every time we scrape it, we need to parse this data, and we need to allocate new string object. So it would be really nice if we can store this unique object only once, not every time. And this is called string interning, when we allocate a new object for unique string only once, and all subsequent scrapes or scrapes for other targets will only refer to it. And this approach helps us to save some memory during scraping. And this is naive implementation of string interning. It's super simple. It's basically a cache based on a hash map. So hash map uses string as a key and a value type. And then you have intern function, which checks if we already have the string in cache. If yes, we return this object. If no, we save it. So this is how string interning works in practice. We have completely two equal strings, but generated in different methods, S1 and S2. We intern them, and now they are pointing to the same object. So these techniques help you to save some memory. But it is not really production ready. First, this hash map is not thread safe. You can't access it from many Go routines. So probably you want to add lock mutex. But mutex will not scale with multi-core systems when you have a lot of threads, a lot of CPUs doing the same work. There will be a contention on access to this map. So the better solution would be to use sync map from the original standard Go package. And intern function becomes even simpler with sync map. What Go docs say about sync map? Well, they recommend to use it when you write once but read many times the entry. Basically, this means that use sync map when you expect high cache hit rate. So if you expect high cache hit rate, it will work really well for you. And also is that optimized for concurrent access from multiple Go routines. So it will outperform performance for standard hash map with lock on multi-core systems. Okay, what are gotchas with having this map? Like with any cache, this map will grow over time because your data isn't static. Data is changing all the time. You will have more and more keys all the time, and this map will grow and grow, consuming more and more memory. So you need to come up with idea how to control the memory usage. So probably you want to rotate this map once in a while, replacing it with blank one. Or maybe you want to introduce something more complex, like time to leave logic, and periodically purge those entries which never were requested. And also, I would recommend to check arguments passed to intern function for sanity, because at some point of time, someone will pass unsafely converted byte slice, which is mutable. Or maybe someone will pass a substring. And if you intern substring, the piece of bigger string, it will point to wrong object. So each time you decide to save the string into internal map, please clone it. It will save you from some subtle bugs. Short summary. So in vectorial metrics, we use string interning for storing this metadata from the parsed metrics. It helps us to reduce memory usage during parsing, and it works really good for read-intensive workload, where the number of variants that we need to intern is limited. And with metric names, with metric labels, it is a case, because metric labels are not changing that frequently. OK, another optimization, functions, results caching. It is also really simple. So in vectorial metrics and in Prometheus, there is a thing called relabeling, which basically allows users to modify the data that they scrape before it gets to database. So for example, we want to replace all dashes in label name with underscores to make them uniform. And this transformation will happen each time you scrape some metrics. But it will happen each time for the same label names, right? So it would be nice if we don't do this all the time for the same data. So internally, we have something called caching transformer, which also maintains this async map cache. And it also can be instrumented with transform function, which is user-specified function to do some transformation of a string. And here's how this transform function works. So we check, we accept this string that we need to transform. We check if we already transformed it in the past, if we already have the cached result for it. If yes, it is a happy path, we return a result. If no, we invoke the transformation and cache the result. And here's how it works in practice. So, for example, we have some variable called Prometheus sanitizer, which replaces all chars not supported by Prometheus with underscores. And here's how we invoke this function. So we have public sanitize name, which is applied to everything that we scrape. Sorry. So quick recap. This caching transformation helps us to save CPU time, but everything comes with cost, and we pay for it with increased memory because we need to maintain these caches in the transformer cache. It works the best for string transformation or for regex matching, and it's also really good when you have this, again, limited number of variants, because as any cache, you want to be efficient and you want high cache hit rate. So it works really good when parsing labels, but it doesn't work good for query processing, for example, because, again, queries are unpredictable. User can request completely two different data sets at one time, and if you cache them, you will get no benefits. You will only spend extra resources on it. OK, limiting concurrency for CPU-bound load. So remember I said that ingestion is kind of flatlined, but it's not always like that. You don't need to expect it will be always like that. So here we have like a daily fluctuations of the number of targets we scrape. And margin is about 10,000 targets. So in the evening we have like 90K. In the morning we have 100K that we need to scrape. The same happens with ingestion. There are sometimes really huge spikes of the metrics we need to process because someone deployed a new application, new set of applications, and they expose new metrics. Or just because of a mistake in metric names or something like that, something generated like a really huge spike of data that we need to process. And what we want to have with that, we want to be protected that these spikes will not crash our time series database. So we want to make sure that we are stable and remain efficient even if there is ingestion spike. So, and limiting concurrency, exactly a thing which helps us to control memory and CPU usage, and also to remain efficient. Because if you don't spawn like thousands of Go routines for doing CPU-intensive work, if you spawn only a limited number, usually equal to the number of CPU cores your machine have, you will reduce in the probability of context switches. And context switches is the thing which could consume extra resources and spend time for not doing efficient work. The downside of limiting concurrency here is that you can easily make a mistake. For example, if you apply limiting concurrency for I/O operations, you can end up with the situation when one worker waits for response from disk or network, and disk or network are unpredictable, unstable. They can introduce a lot of delays, and that means that your worker will be just doing nothing, waiting for network to respond. So this is why it is usually used for CPU-intensive work. This is the common implementation of concurrency limiting. So you define a limit as a number of CPUs, and then you spawn this specific number of workers for data processing. And you feed those workers with some work channel or something, which distributes the work across the workers. This is like nice approach. You can also benefit from the notions that you have these workers. You can instrument workers with scoped buffers, for example, for data processing. You can instrument them with metrics or some other stats information. But it also becomes more complex to use it like that, because you now need to start those workers. You need a procedure to stop workers, to drain their channels. You need also to pay attention to synchronization via channel. And this could be like a pain if you have really small units of work to process. Channel may become a point of contention for distributing this. So there is a simpler approach for doing that. Well, you basically define a buffer channel with length limited again to the number of CPU cores. And this channel works like a token machine, and like a set of tokens each coroutine needs to receive before doing some work. So when we start some expensive processing in func process data, we first check if we have a free token to do the work, if we have allowance to do the work. If we do, we continue with heavy processing. If we not, we just block and waiting for a new token to appear in this channel. And with this approach, you can be sure that at any moment of time, you have not more than amount of tokens of concurrently running coroutines doing some expensive work. And this is much simpler than running separate workers. OK, quick summary. So this works the best, again, for CPU-bound operations. You don't want I/O to be involved in this. Limiting concurrency helps us to bound resource usage. You can be sure that at any moment of time, not more than n coroutines allocating data or doing some CPU-intensive work. And this also reduces the probability of context switches because you have low contention. Each coroutine will be scheduled to separate CPU core, and they will be as efficient as possible. And yeah, don't do this for I/O. OK, sync pool. So sync pool can be used in multiple scenarios. This scenario is the ideal. Ideal scenario is when you receive the object from sync pool and release this object in the same coroutine, so it doesn't escape. Why it is cool? Because in internal sync pool implementations, there are inner pools for storing the objects. And those pools are mapped on threads in Go runtime. And when you request an object from sync pool, it first checks the inner pool on this thread where coroutine runs. And if it doesn't find object there, it tries to steal it from other threads. And this could take some time. If it doesn't find it, if it can't steal it, it will invoke the new function. So the ideal case is when you request object and release object in one coroutine. That's how you reduce the probability of object stealing. And of course, it reduces the garbage collection pressure because you do less allocations with sync pool. That's why it exists. Not ideal case, but still viable, is when object is retrieved and released with different coroutines, where you receive object, pass somewhere else, and then it gets used and released. So this scenario also can reduce the garbage collection pressure, but there is a higher probability that object will be returned to another thread, so it will be in another subpool, and increases the probability of object stealing when using sync pool. And not really good scenario again, I/O, because as I said, I/O is unpredictable, and you can end up in situation where you invoke get or put methods of sync pool not in balance, because networks start lagging and you invoke more new functions than put functions, or opposite, you invoke more put functions than get functions. In this case, you can end up with the higher memory usage than expected, or with bigger amounts of objects in sync pool than expected. So it's better to stick to ideal case where number of calls to get and put is balanced. This is how you get the best performance from sync pool. Okay, inside vector metrics we also have implementation of byte buffer based on sync pool, and byte buffer is really commonly used across the whole code base, because we use it for decompressing data blocks, for parsing metric names and label names for many cases. And here's how many interfaces it supports internally. And this is how we use it. So we request a byte buffer from the pool. We do expensive work with decompressing, for example, that standard compressed data block. We process the data and we return it back to the pool. This is like the ideal case for using sync pool if we need to decompress thousands of blocks to make some read query. We do it really efficiently because at this moment of time, all blocks are already read. We don't wait for disk, we just do CPU-intensive decompressing work. Okay, what are gotchas with sync pool, and especially with byte buffer pool? Is that sync pool assumes that all entries you put into it are the same. But in real life, all these byte buffers could be of completely different size. And mixing these big and small byte buffers could result in excessive memory usage or just in suboptimal usage of this object. So imagine that you had to decompress one really big blocks, but all other are really small. And now in sync pool, you will have really big byte slice, which then will be pinned by other coroutines, constantly reused, but underutilized. So you're using only 10% of this block, but you still keep it in the memory. Or opposite, you're receiving smaller object than you expected to receive, so you need to expand this slice. So you're again spending CPU time and you again allocate. What could be done better? You can use leveled or bucketized byte buffer pools. So what it means is it means that you can have sync pool for each specific size. This is what we have internally in vector metrics, and we have 17 buckets, and each bucket represents its own size. And here's how we use it. So remember again, I talked about scraping data, and you could have one target which exposes 1,000 metrics and another target which exposes 10,000 of metrics, and you need to parse them both, and they need different buffers, different buffer sizes to do this processing. So what we do, we remember what was the previous page size, and based on this page size, we request a byte buffer of this specific size. And for big targets, we receive bigger byte buffers. For small targets, we receive smaller byte buffers. This is how we are not mixing them, and this is how we are not spending time on expanding byte slices if we need to expand. Okay, if you want to know more about internal processing in vector metrics, how processes are parallelized, how vector metric scales, I encourage you to check this talk from our CTO about scaling vector metrics to 100 million samples per second on ingestion. It is also really full of technical details. Okay, and quick summary about what we learned. The first, string interning helps you to reduce garbage collection pressure and helps you to reduce memory usage, but only when used right for read-intensive workload. For queries, in our case, it shows it more expensive than not using, so be wise. Function results caching for regex matching and for strings transformations helps us to reduce CPU usage. in cost of increased memory usage. So everything has a price. Concurrency limiting helps us to keep our database under control, stable, even if there are ingestion spikes or expensive queries, and also to get the best performance we could with multi-core systems. And sync pool helps us to reduce garbage collection pressure and improves performance, but again, only for CPU-bound operations. Okay, that was mostly all about optimizations we use internally. If you have any questions, I would be glad to answer.